Guys, so today we're going to talk about piecewise defined functions, and that should be review. I'm sure you've seen piecewise defined functions at some point earlier in your life, but really what we're going to do is we're going to use piecewise defined functions as a vehicle for talking about continuity, which is a concept we introduced a couple weeks back. So let's just begin. This is the worksheet that I've given you for this lesson, and we're going to use these notes throughout the worksheet as class notes. So first of all, what is a piecewise defined function? A piecewise function is simply a function given by more than one formula. Okay, so for example, this thing here is a piecewise defined function because, as you can see, there are three different formulas. One of them is x squared, one of them is 2x, and the third formula is a little bit funny. It's just a constant 5. Now, if you have a function with, say, three different formulas, you need to ask yourself, which formula should you be using? The answer to that question is provided by these things here: the x less than 2, the x equal to 2, and the x bigger than 2. What this is telling you is that if your input to the function, if your x value is less than 2, then you're going to be using this first formula here, x squared. If your input is bigger than 2, if your x value, your input, is bigger than 2, then you're going to be using this formula here, 2x. And if your input is exactly 2 on the nose, then the output is actually just 5, right? I mean, that's not exactly a formula, right? It's just saying that if you plug in 2 to the function, then you're going to get out 5 as an output. So just as a quick example, if I asked you, what is f of negative 3? Well, the thing is, negative 3, your input, is less than 2, right? Which means that you should be using the first formula here, x squared. So because our input, negative 3, is less than 2, we should be plugging negative 3 into this first function here. So we're going to plug negative 3 into x squared, and we're going to get 9, right? Okay, what is f of 4? Well, here your input 4 is bigger than 2, therefore you should be using this third formula here, right? So you plug 4 into this formula, the 2x, you get 2 times 4, which is 8. And finally, if I asked you what is f of 2, you would say, oh, well, it's 5. Okay, so that's a review of what piecewise functions are. But now I want to talk about graphs of piecewise defined functions, and we'll consider just an example here. Consider the piecewise function f of x equals, and then we've got these two different formulas, right? This first one applies when the input is strictly less than 3, and this second formula applies when the input is bigger than or equal to 3. So what does the graph of this thing look like? Well, basically, on this region here, on the region x less than 3, the graph of the function just looks like this, which is a line, right? It's a line with slope 1 and y-intercept 1. And over this region here, when x is bigger than or equal to 3, that's to the right of 3, the graph looks like this line here. Well, if you really wanted to construct the graph of this function, then what you would do is the following. You would graph each one of these functions. Both of these are lines, right? So you would graph both of those lines, but then you would kind of erase the portion that you don't want to actually draw. Let me show you what I mean. So here I've got Desmos in the other window, and I'm going to just start by typing in that first formula, the x plus 1. I have y is equal to x plus 1, and there's the line. But remember that this formula is only supposed to be applied when the input x is less than 3. You can actually have Desmos only graph the function you've inputted by in braces, typing x less than 3. So now you can see that the line is only drawn over the region x less than 3. In other words, this line is being drawn to the left of 3, okay? So what I did is I just graphed this line here, x plus 1, just like I ordinarily would, so I just graphed that line, but then I said, oh wait, I'm not supposed to graph that line over the entire x-axis, I'm just supposed to graph it over the region x less than 3, so if this were a piece of paper, what I'd be doing is I would be erasing this portion of the graph here, so that all that remains is the appropriate portion. And then I just have to do the same thing with this graph here. To the right of 3, I'm going to draw y is equal to negative x plus 5. So I'll start by just graphing y equals negative x plus 5. Of course, that's a line with slope -1 and y-intercept 5. But then I say to myself, wait, I don't actually want to graph that entire line. I just want to graph the portion of the line which sits above this region here, the x bigger than or equal to 3. And I can have Desmos do that by typing in x bigger than or equal to 3 in braces. So here's a graph, and there's not really any good reason for these to be two different colors. I'll go ahead and make both of them black. So this is a reasonable but actually incomplete graph of our piecewise function. It's almost complete, but there's one big problem. Okay, let's pretend for a moment that we didn't have this formula. Okay, and suppose that the only thing you had was this graph right here. Okay, and suppose I asked you, what is f of 3? Like, what is the value of the function at 3? Well, you would go over to 3 on the x-axis, and then you'd sort of look up and see the y value of the graph. The problem is that there appear to be two different y values associated with this input of 3, right? So from this graph alone, as it's currently drawn, it looks like f of 3 could be 2, right? Looks like it could be 2, or maybe it could also be 4. And that's really a problem because remember, functions are supposed to have only one output for every input, right? The value of the function at 3 has to be either 2 or 4 or neither, possibly, right? It can only have one value. Now, we know from the formula, so I hope that I've convinced you that this graph isn't quite complete because of that ambiguity around 3. If we return to the original formula, we see that when it comes to x equals 3, when the input is 3 exactly, we should be using this second formula, right? When x is bigger than or equal to 3, we should be using this second formula. So it is that second line, this one here with the negative slope, that's the line which should be applied above -3 and not this other line, okay? In other words, the value of the function at 3 is actually 2 and not 4. Now the question is, how do you represent that graphically? What you have to do is you use these full and empty circles. So I'm going to go ahead and do that. Now I want a full circle here because the value of the function at 3 is 2. So I'll type 3, 2. There's my full circle. And then I want an empty circle here. At 3, 4, I have to go into Desmos and make that an empty circle. Okay, there we are. Now it's an empty circle. So this is now the complete graph, and I hope that you now see the necessity of the full and empty circle, right? They tell you what the value of the function is sort of at this boundary point where the two pieces match up. And by the way, this is the correct graph for this function, but as you've seen from the graphs, right, it's totally possible that the value of the function at 3 isn't 2, nor is it 4. It could be something else, like it could be 5. And the way that we would represent that is by putting an empty circle here and putting a full circle at 5. So if I went ahead and made this empty, that one's already empty. It's this one I need to change. Here we are. And then add a full circle at 3, 5. That would be saying that the value of the function at 3 is not 2, nor is it 4, but it's actually 5. Okay, there was some confusion about that on one of the previous worksheets, so I wanted to make that clear. Okay, so we've reviewed piecewise defined functions and their graphs, and I now want to proceed to using piecewise defined functions to talk about continuity. We talked about continuity in a graphical context, right? Roughly speaking, a function is continuous at a point if there's no gap at that point, no hole or gap or anything like that. But if you remember, there's really this formal technical definition of continuity, right? Remember that the actual definition of continuity is the following. We say that a function is continuous at C if the continuity equation limit as x approaches C, f of x is equal to f of C. This little equation here, that is what needs to happen in order for the function to be continuous at c. What we're going to do is we're going to be using this definition to analyze the continuity of piecewise defined functions at their boundary points. In other words, at the point where the different pieces of the piecewise function meet. So we'll begin with this example here. We have this piecewise function, three formulas. I think it might even be the exact same one that we had at the very beginning of the lesson, or something like it. So here we have this piecewise function. And the question is this function continuous at the point x equals 2? Now, one way of doing this, I suppose, would be to just graph it, right? If you graphed the whole thing, then you could look at it and sort of say, are there any holes or anything? Or are there any breaks at 2? That would be a way of doing it, but I want to show you how to do this purely algebraically without drawing a graph. And the truth is, this is the proper way of showing that the function is continuous, by using the definition of continuity, okay? So in order for the function to be continuous at 2, this equation needs to hold, where c is equal to 2. Okay, c is the point at which you're trying to investigate continuity. We're trying to investigate whether or not the function is continuous at 2, so c is 2. So the function is continuous at 2 if and only if this equation right here holds. Limit as x approaches 2 is equal to the value of the function at 2. And you might remember that in order for this equation to hold, in order for this equation to be valid, 3 separate things need to actually take place. Okay, first of all, this side of the equation must be defined, right? That's a two-sided limit. And as you know, two-sided limits often aren't defined because the left and right-hand limits could be different, right? So first of all, this left side of the equation must be defined, right? The two-handed limit must be defined at 2. Second of all, this side of the equation has to be defined. That, of course, is the value of the function at 2. Well, if the function is undefined at 2, then you've got a problem, okay? And finally, even if this side of the equation and this side of the equation are both defined, they have to be equal. They have to agree, okay? And that's the third thing that you have to check. So in order to check the continuity at this boundary point x equals 2, where the different pieces of the function line up, you have to really investigate 3 things. Number 1, is the two-sided limit as x approaches 2 defined? Number 2, is the value of the function at 2 defined? And number 3, assuming those other 2 things are defined, are they equal? Okay, so let's just do each of those 3 things for this function here. Part 1, we're going to check that the limit as x approaches 2 is defined. And we have to recall under what circumstances is a two-sided limit defined. Remember, the two-sided limit as x approaches 2 is only defined if the left and right hand limits agree. In other words, if they're equal, right? This is a two-sided limit because there's no plus or minus in the superscript here for the 2. So it's a two-sided limit. In order to be defined, the left and right hand limits have to agree. So what we're going to do is we're going to look at the left and right hand limits as x approaches 2 for this function, and we're going to see if they are the same or not. If they're the same, then the two-sided limit is defined, and if they're different, then it's not. So let's start with the left-hand limit, okay? We're going to look at the limit as x approaches 2 from the left, right? Now here's the problem. You have to be careful with this. We want to let x approach 2 from the left, and normally when you want to evaluate a limit algebraically, what you do is you just plug the value into the formula, right? That's the first thing you try anyway. Remember from last week, you want to evaluate a limit algebraically, you have to plug the number in and see what you get. The trouble is, this is a piecewise function. There are 3 different formulas, right? There are 3 different formulas for this function, and so you should ask yourself, well, wait a minute, which of those formulas should I be plugging into? Should I be plugging 2 into the first formula, or the last formula, or the middle formula? What should I be doing? When you think about it very carefully, x is approaching 2 from the left, okay? What that means is that x is like over here, and it's getting closer and closer to 2 on the left. So if x is approaching 2 from the left, that means that x is actually less than 2. Does that make sense? If x is approaching 2 from the left, like over here, that means that x is actually less than 2. And if x is less than 2, that means you should be using this first formula. In other words, to evaluate the limit as x approaches 2 from the left-hand limit, we need to plug 2 into the first formula, x squared, okay? So we're going to use that first formula. We plug 2 into it. We have 2 squared. That's 4. Okay, so the left-hand limit is 4. How about the right-hand limit? Now we need to look at the limit as x approaches 2 from the right. Well, if x is approaching 2 from the right, that means that x is somewhere over here. X is approaching 2 from the right. That means x is over here. That means x is actually bigger than 2. Okay? And if x is bigger than 2, then we should be using this third formula here. All right? Therefore, in order to evaluate the limit as x approaches 2 from the right, we should be plugging into that third formula, the 2x right here. We should be plugging into that third formula, 2x. And if we do, we get 2 times 2, which is 4. Now, in this case, the left-hand limit was 4. The right-hand limit was 4. Okay, the left and right-hand limits agree. That means the two-sided limit is indeed defined, and it's just 4, okay? But in a different problem, these two numbers could have been different, in which case this thing would be undefined, and that would mean the function is not continuous, okay? But in this case, left and right-hand limits agree, therefore the two-sided limit exists. So, well, that's part 1 of checking that f is continuous at 2, right? Part 2 is a lot less work, okay? We have to verify that the function is defined at 2, okay? All we have to do is just sort of go back to the formula. Is there a rule that makes sense for plugging in 2? Like, if we plug in 2 into this function, do we have a value? Yeah, it's 5. Right? It's defined very explicitly. It's kind of singled out. This line here is just telling you, hey, if you plug in 2, you get 5. So is the function defined at 2? Yeah, it's definitely defined at 2. It's 5. Okay, so the second thing that we have to check is good, right? It checks out. The function is defined at 2. But then remember, there's one more thing to check, right? Even though the two-sided limit is defined, and even though the function is defined at 2, those two things have to be the same. But if you've been paying attention, you've probably already noticed they're not the same. The two-sided limit was 4, but the value of the function at 2 is not 4, it's 5, right? So because those two things are different, this continuity equation here fails, which means the function is not continuous at 2, okay? So what we saw in this case was that, this guy here is defined and this guy here is defined, but they aren't equal, right? So that's one way that continuity can fail to occur, okay? But there's other ways, right? Sometimes this thing won't be defined, or sometimes this thing won't be defined. It all just depends on problem to problem. So let's go ahead and do one more example. So here I have another piecewise defined function, 2 formulas here, this one for x less than 3 and this one for x bigger than 3. And I'm going to ask you, is the function continuous at the boundary point at x equals 3, where these two pieces meet? So, I'm not going to go through the whole thing in quite as much detail, but once again, we have to check 3 things, right? We sort of have to check, is the two-sided limit defined? Of course, in this case, it wouldn't be x goes to 2, it would be x goes to 3, right? But same idea. So first of all, we just have to ask, like, is the two-sided limit at 3 defined? And just like before, we have to ask, well, what are the left and the right-hand limits? Well, if you want to look at the left-hand limit as x approaches 3 from the left, okay, if x is approaching 3 from the left, that means that x is over here, which means that x is less than 3, which means that we should be using this first formula here. Okay, so if we plug, so we're going to plug 3 into that first formula, x plus 6, that gives us 9. For the right-hand limit, x is approaching 3 from the right. Okay, that means that x is like over here, which means that x is bigger than 3. So we would be plugging 3 into this second formula here, okay? And if you do that, you get also 9. Okay, that tells us that because the left and right hand limits agree, the two-sided limit exists and is equal to 3, right? Okay, so the two-sided limit exists, but that's just the first thing you have to check, right? To see if a function is continuous at the point or not. We then have to ask, is the function defined at the point? So is the function defined at 3? The answer is no. There is no rule for when x is equal to 3. There's a rule for when x is less than 3. There's a rule for when x is bigger than 3. But there's no rule for when x is exactly 3 on the nose. This function is undefined at 3, and therefore the function's not continuous at 3. That's the end of the story. Now, incidentally, if I changed, say, this greater than sign to a greater than or equal to sign, like that, now the function is defined at 3. It's saying, hey, if you want to evaluate the function at 3, you use this formula, right? In that case, the value of the function at 3 would also be 9, and the function would indeed be continuous, okay, because everything matches up. Now, that's all kind of abstract, and I have two things to say before I finish up. This seems rather complicated, but in truth, it's a pretty straightforward thing, checking continuity at the boundary point of a piecewise function. All you really have to do is make sure that, these three things match up, okay? At the boundary point. This thing evaluated at 2, back to our first problem now. This formula at 2 is 4, that's good, okay? This formula at 2 is 4, okay, that's cool. But then this formula is not 4, so it's not continuous. It really is that easy. But the thing is, we're going to ask that you really state carefully why exactly the function is or isn't continuous. And in the worksheet, what I've done is I've given you kind of a guide for exactly what we want you to write when analyzing the continuity of a function. We really want you to use the limit notation. We really want you to draw conclusions like, therefore, the two-sided limit exists and blah, blah, blah. We don't want to see just you write down a couple of numbers and then say yes or no, okay? We really want to see an explanation. And here in exercise 2 of the worksheet, what I've done for you is I've given you this piecewise defined function, and I've pretty much written out exactly what you should be writing out, right? What should you be doing? You should first be making sure that the two-sided limit exists, which means you have to look at the left-hand limit, right? So you're going to look at the left-hand limit, and then you're going to say, oh, well, I'm going to use the first formula. You plug in 0, and you get, and then I've got a blank space here for you to fill in, okay? And then you're going to look at the right-hand limit. You're going to see what you get, and then you're going to conclude that the two-sided limit exists is blah. Then you're going to look at the value of the function at the point that's checking that the function is defined at 0, right? And then you're going to compare them. This structure here is what we're looking for, okay? So make sure that you carefully duplicate that language and that notation when you do the problems here. I've given you a bunch of space because we're not looking for just yes or no. You're going to duplicate this stuff here down here, okay? So that's it. I hope everybody is doing well. Oh, and at the end of the worksheet, there's some review problems, right, from earlier weeks. There's another chance for you to try that tricky graphing problem where you had to draw the single graph that had all these different properties. It's another one of those. You'll have another shot at it. And then we've got some problems from last week's work. I mean, they're not exactly problems from last week, but they're of the same type. Evaluating limits algebraically. So for these guys, you're going to have to, basically, you're going to plug in the number, right? And you're probably going to get 0 over 0. Let's be honest. That's what you usually get. And you're going to have to rewrite the function. Maybe factor and cancel common factors or whatever you have to do, okay? All right, well, hope you